Welcome back to the AI Research Roundup. I am your host, Alex. Alright, today we're diving into a fascinating paper from the Papers with Code trending list, published on May 18th, 2025, titled SOAP, Style-Omniscient Animatable Portraits. So, this paper tackles the challenge of creating really expressive, animatable 3D avatars from just a single image. What's cool is that SOAP aims to work across many different artistic styles. Think realistic, cartoon, or even anime, and it's designed to handle tricky things like detailed hairstyles and accessories. The goal is to produce 3D models that are well-rigged, meaning they have an internal structure that allows for natural-looking animations like facial expressions, eye movements, and even lip motions. And for those keen to see this in action, it's great the researchers also released the code for SOAP. Alright, so over on their GitHub page, you can grab the source code and installation steps. They've even got a graphical user interface, or GUI, which is a visual tool for visualizing and interacting with the generated face shapes. Okay, so this first figure, figure 1, really shows off what SOAP can do. On the left, you see these diverse input portraits. One's a cartoon, another is a classic painted style, and there's a more realistic older gentleman. Then, in the middle, we see the 3D animatable avatars that SOAP reconstructed from just those single images, shown from a couple of angles. And importantly, on the right, you can see these avatars animated with various facial expressions, really bringing them to life and demonstrating that well-rigged quality, complete with eyeballs and teeth. Okay, so after seeing those impressive results in Figure 1, Figure 2 here shows us the SOAP method's pipeline. It kicks off with Style-Omniscient sparse-view generation. From the single input portrait, the system creates 6 different viewpoints. These aren't just color images. They also include normal maps, which are images encoding 3D surface direction, crucial for defining shape. Next, in the animatable 3D head optimization stage, it uses these views to deform an initial flame mesh, a standard animatable 3D head model, to match the input, correcting the mesh's structure or topology as needed. Finally, it adds eyeballs, teeth, and generates the texture for the complete head. Alright, so that style-omniscient sparse-view generation we just discussed, it relies on a really diverse dataset for training. Figure 3 here gives us a peek into this 3D head dataset. The core strategy is to train the diffusion module, which, as we recall, helps generate those multiple viewpoints, using only 2 extreme styles. You can see examples of highly realistic heads on one side and then very distinct anime-style characters on the other. The idea is that, by learning from this large difference, the model can then generalize to various unseen intermediate styles, like those shown between the extremes. Okay, so with that diverse dataset established, the next step is the animatable 3D head optimization. Figure 5 here shows us the different loss functions that guide this optimization process. A loss function, in machine learning, is essentially a way to measure how far off the model's current attempt is from the desired result, and the system tries to minimize this error. First, there's the reconstruction loss, labeled LREC. This uses those multi-view normal maps, which we know define the 3D shape, and also applies Laplacian smoothing, which is a technique to keep the mesh surface smooth and natural looking. Then we have the semantic loss, or LSMA. This uses predicted parsing maps, which are like segmented images showing which part is hair, face, and so on. And also eye masks, to ensure that corresponding parts deform correctly. And finally, the landmark loss, LLMK, uses key facial points to preserve the structure of features like eyes and mouth, and also helps maintain facial symmetry. Alright, so those loss functions we just discussed guide the overall shaping of the 3D head. But Figure 4 here really demonstrates why another part of that optimization process, specifically topology correction, is so vital. Topology, in this context, refers to the fundamental structure and connectivity of the 3D mesh. Looking at the figure, with the input portrait on the left, the top row shows normal maps of the optimized mesh without this topology correction. You can see how it struggles, especially with the hair, leading to undesirable twists and a failure to capture fine geometric details. The bottom row, however, shows the results with topology correction. As the N value increases, likely indicating a more refined mesh with more vertices, the geometric details of the hair and face are much better reconstructed. This step is clearly crucial for getting those complex shapes right. Alright, so those loss functions and topology correction we've been discussing really seem to pay off when we look at the numbers. Table 1 here gives us a quantitative comparison of SOAP against other methods across different styles. It uses several metrics to measure performance. For instance, we see peak signal-to-noise ratio and structural similarity index measure, where higher scores mean better image quality. Then there's learned perceptual image patch similarity, or LPIPS. This is a metric that assesses how similar images appear to the human eye, and for this, lower scores are better. We also have chamfer distance, often abbreviated CD. This measures the geometric accuracy of the 3D shape, so a lower chamfer distance is preferable. And Fréchet inception distance, or FID. This evaluates the realism of the generated images, with lower values indicating more realistic results. Looking at the hours row, which represents SOAP, it consistently achieves strong scores across most of these metrics, often outperforming the other listed methods. So, those strong quantitative results we saw in the table, well, figure 7 here gives us a visual taste of what that means in practice. This figure showcases the animation capabilities. We're seeing expressive and stylized 3D avatars, each row representing a different character, animated using flame parameters. Flame, which stands for faces learned with articulated models and expressions, is a parametric 3D head model that allows for detailed control over facial shape and expression. And you can see here how SOAP generates these diverse facial expressions, from subtle shifts to more pronounced ones, across very different artistic styles. And those expressive animations really highlight the power of SOAP. So what we've seen today is a method that can take just a single stylized portrait and impressively turn it into a fully animatable 3D avatar across a huge range of artistic styles. This is a really big step for creating personalized digital characters and for, well, creative expression in general. That's all for this AI Research Roundup. Thanks for tuning in. I'm Alex.